Alright, today we're going to be doing Gibbs free energy. Alright, so to understand Gibbs free energy, let's first go to its components. So Gibbs free energy essentially is the enthalpy, or heat of formation, minus the temperature times the entropy. Now it sounds very intimidating. Let's explain what these are. Entropy is essentially the disorder in a system, and it's kind of like the spontaneity of reactions happening with different chemicals. So the unit for entropy would be joules over moles times Kelvin. And enthalpy, or heat of formation, is the energy needed for a chemical to form. So, for example, you need a certain amount of energy in a reaction to make that reaction happen and make the product. And the units for that would be kilojoules over moles. And what is Gibbs free energy? Well, we're going to explain. And the units for that is also kilojoules over moles. So the first thing you need to understand about Gibbs free energy is it explains the likelihood of a certain reaction happening. So let's go to this table over here to explain that. So you have this essential equation, delta G equals delta H minus temperature times delta S. So here we have it. If the heat of formation is low and the entropy is low, then most likely the chemical reaction is going to happen at low temperatures more often. And if the heat of formation is low but the entropy is high, then this reaction is almost always going to happen. Because think of it like this. The reaction needs a certain amount of energy to happen, a small amount, and there's a lot of energy in abundance from the entropy. So therefore it has a lot of supply, little demand, and it's easy for it to happen. Now, if the heat of formation is very high, but the entropy is very low, then it's the opposite. It needs a lot of energy, but it doesn't have as much energy, so it's almost never going to happen. Now, if the heat of formation is very high and the entropy is also very high, then this reaction is most likely going to happen at high temperatures. But just like the first one, it's not exclusively high temperatures, and in the first one, it's not exclusively low temperatures. It'll just happen more spontaneously. Now, the second part of Gibbs free energy is where we get into the actual math. Here we have the reaction of hydrogen peroxide making water and oxygen. So you have 2H2O2 equals 2H2O plus O2. Now, you have the different components. You have the heat of formation for each of the chemicals and the entropy for each of the chemicals. Now, for heat of formation, it's in kilojoules over moles, which is the same unit as Gibbs free energy, so we can leave that alone. Actually, let me just change that to O2. That was dumb. It's 0 kilojoules per mole is required to make O2. Now that that's clarified, for delta S, or entropy, the units are in joules over mole times Kelvin. However, Gibbs free energy is in kilojoules, so we have to convert that to kilojoules by dividing it by 1,000. So here we go. Now, to find the enthalpy, or the heat of formation of the total system, you have to do products minus reactants. So the reactants here is hydrogen peroxide is reacting to create the products H2O and O2. Here, because there's two H2Os, you have to multiply its enthalpy by 2. That value, you subtract that by the value of H2O2. So let's calculate that really fast. That would be about negative 188.26 kilojoules per mole. Excuse my handwriting. Now for entropy, you do the exact same thing. You multiply the H2O value by 2, add it to the oxygen, you have the products together, and subtract that from the reactants. You have to multiply that by 2 because you have to remember there's two H2O2s. And the answer you get for that one would be 0.05716. Now you don't have to be this accurate most of the time. You can round to a certain degree, but for the sake of math, I'll write it all out. Now we're back to the original equation for Gibbs free energy. So let's put together the values. Now temperature factors in here, so we'll have to go back to the temperature. This is happening at 25 degrees Celsius, but the temperature for this equation is actually in Kelvin. So 25 degrees Celsius would be about 298 degrees Kelvin. Alright, so let's put it together. We have the heat of formation, negative 188.26 minus 298 degrees Kelvin multiplied by 0.05716 joules over mole Kelvin. Now, just like to show you that, actually I'll write it out. Gibbs free energy is kilojoules over moles, G equals delta by H, which is also kilojoules over moles, minus Kelvin times kilojoules over moles times Kelvin. So you see here, it all actually makes sense because there's Kelvin's